I'm addicted to collecting Pokemon cards. I got back into the physical TCG back in September, and then the Pokemon Company went and fueled my chronic gambling habits further by releasing Pokemon TCG Pocket in late October. Many of the cards, particularly EX cards, have this super cool parallax effect where parts of the artwork and background appear to be on separate layers which move differently when the card is rotated, together with an impossible window effect where the layers are only visible within the card's border bounds. In this tutorial, I'm going to recreate this effect with the stencil buffer, which you might remember from my impossible geometry video. Plus, I'll implement a holographic rainbow shine effect where the reflections move as the card rotates. I'll be doing all of this in Unity 6. Here I have set up a test card already. It's made up of 4 main layers. The card's border graphics in the middle, which uses alpha clipping to create the hole in the center. Then the Pokemon artwork on a second layer moved slightly forward, which is transparent. I'm making a hard read that Generation 10 will have a Goose Pokemon, of course. Then there's the background layer offset behind the other layers. You'll see that the background is much larger than the others, and that's because it still needs to be visible inside the border bounding box when the card rotates. This layer can use opaque materials. And finally, a layer with all the text elements which is flush with the border and once again uses transparent text materials. First, let's think about how to mask out the foreground and background layers so that they only appear inside the card borders. We can do this with the stencil buffer, which lets us store a little extra data about each pixel. Essentially, we can draw a quad mesh that fits neatly inside the border, but we don't want it to draw any colors to the screen. Instead, we can write an unsigned 8-bit integer into the stencil buffer. That's a value from 0 to 255. By default, all pixels have a stencil value of 0, so we can write a value of 1 instead wherever this masking mesh exists. Later, when we render the foreground and background meshes, we can read the stencil buffer values for each pixel we're trying to draw. If there is a 1 in the stencil buffer, we know that this is a position where the mask exists, and so we can decide to draw the layer normally. If the stencil value is 0, it is outside the card interior, so we can call that pixel. Unfortunately, ShaderGraph doesn't yet support stencils. Well, lit and unlit graphs don't. Full-screen graphs do, proving the functionality could easily be added, but I digress. There are a few approaches we could take to write a stencil, but I'm going to write a stencil mask shader using good old HLSL. I'll right-click in the project view, select Shader, Unlit Shader. The actual preset you choose doesn't hugely matter, and let's name the shader Stencil Mask. This isn't what you'll see when you open the file, this is the finished shader. I won't go through it line by line, but it's actually very short. The main parts are the integer property at the top called StencilRef. This is the value that I want the mask mesh to write into the stencil buffer. Then, inside the pass block, you'll see a new stencil block. The ref value is short for reference, so we use the StencilRef property. Next, we have a comparison function, comp. This means that we are going to compare the reference value with the stencil value already inside the stencil buffer. This is called the stencil test. To remind you, by default, that's 0. We can use many comparison functions. Greater, where the test passes if the reference is higher than the current value. L equal, where the test passes if the reference is lower or equal to the current value, and so on. Never will always fail, and always, which I've chosen to use, will always pass, regardless of what the reference or current stencil values are. Once the test has passed or failed, we need to decide what to do with the stencil buffer. With the pass keyword, we specify what happens when the stencil test passes. We can zero out the value, increment it by 1, decrement it, and so on. But we're going to replace the existing value with the reference value. It's the same story for when the stencil test fails. In that case, I've chosen the default behavior, which is to keep whatever value is already in the stencil buffer. The last really important thing to do is turn off writing to the depth buffer, because we still want to render things behind the mask mesh. We can do that with Z right off. I have also added color mask 0, which prevents Unity from writing any color data to the screen, but it's redundant since we haven't actually added any code that would write anything to the screen. Now we can add a mask mesh to the test card and add a material using the mask shader with the stencil ref set to 1. But nothing will happen yet because we're not doing anything to read from the stencil. To do that, I am going to use render objects. Although it's possible to add stencil reading support to an HLSL shader, I don't want to have to do that for every shader I'm using in the game. So I'll stop Unity rendering some of the card layers, then add them back with stencil test spliced in using render objects. Let's create a new layer and name it card artwork or something similar. Then I want to add both the foreground and background card elements to this layer. Next, we'll need to find the project's universal rendered data object, which is where many graphics options can be found. If you create a dual project from the URP template, then you'll find the data asset in Assets, Settings, PC_renderer. Once you've found it, let's go to the Opaque Layer Mask and Transparent Layer Mask options at the top and deselect the card artwork layer from each. Immediately, those parts of the card disappear. Then go to the bottom and click the Add Renderer feature button and add a new Render Objects feature, which we'll use to add the opaque card artwork back. For that, we'll need to set the event to After Rendering Opaques, and then set the queue to Opaque, and the layer mask to Only Card Artwork. The layer will pop back in, but it still isn't called based on the stencil mask. For that, expand the Overrides section and enable Stencil. Some of these options will look familiar after we wrote the stencil mask shader. The value should be set to the same value we set the stencil ref to on the stencil mask material, which was 1. Now, objects in the card artwork layer will compare the existing stencil value with 1, and the compare function should be set to equal. Now, objects in the layer only appear wherever the stencil is equal to 1. Simple. We can add a second render objects feature to add back in the transparent objects inside the card artwork layer. The settings should be the same, except the event is after rendering transparence, and the queue should be transparent. If you'd like to make it easier to distinguish between the two, you can go ahead and rename each of these features, as I have done. I also want to make sure the text always renders over everything else. Currently, the foreground layer renders over the text, and as much as I love looking at geese, I also love reading about geese, so let's do both. We can easily achieve that by adding another layer called card text, which we can put all the text elements into. Then let's go back to the universal renderer data asset and remove this new card text layer from the layer masks at the top of the asset. Then add a third render objects feature. This time, we only need to set the event to after rendering transparence, the queue to transparent, and the layer mask to card text, and our text should pop back into existence and should render over everything else present on the card. Since this render objects feature is lowest down in the list, it will render last, even though it's in the same rendering queue as the second one. If you want to be safe and be absolutely sure that this renders over everything, then you can override the depth and set the depth test to always. Fantastic, that's the parallax effect sorted. Next, I want to create a holographic rainbow effect like you'd see on real Pokemon cards. Depending on how powerful and customizable you want the effect to be, this can actually be fairly complicated, but I'll do my best to explain what each part is doing. I'll make a new shader via Create, Shader Graph, URP, Lit, and name it Card Artwork. If you're copying along at home, you might want to pause this video occasionally because I'm going to gloss over the basics a little. First, let's add base color and base texture properties and wire them up like this. I want to split off the alpha and output it, but we're going to be dealing with mixing the base color and holographic colors later, so let's leave that for now. I will also quickly add a smoothness float property, which is a slider between 0 and 1, and wire this directly to the graph's smoothness output. That will give us a bit more control over the feel of the card surface. Next, let's handle the rainbow pattern that appears on the surface of the card. On a real card, rainbows will appear as streaks across the card, but here in the digital realm, we can do things that real cards can't. I want to animate the rainbow pattern and maybe make it appear noisy and blotchy rather than appearing as neat streaks. To start with the noise pattern, let's add two new float properties: Holo Noise Scale, which will control how tightly packed together the blotches will appear, and Holo Anim Speed, which influences how quickly the shader scrolls through the rainbow hue. I'll make them both sliders for easy usage in the Material Inspector and give them sensible default values. I want the noise pattern to unfold over the card's surface, so I'll add a simple noise node and feed the object space position to its UV slot. If I use the world space position here instead, then the rainbow pattern looks different as I rotate the card. Note here that the UV is a vector 2 and we're inputting a vector 3. This is actually fine, as the shader will use the first two components of the position, XY, and our card is oriented along the XY plane when it's in a neutral position. The Holo Noise Scale property can go right into the scale input. Then we can multiply a time node with the Holo Anim Speed property to create a clock, and add both values. Next, let's somehow convert this into a rainbow. There are two ways we could do this. We could use a color ramp texture, where we encode each color into a thin texture strip, or we can generate the rainbow inside the shader. Our shader will be able to do both. First, let's add a holo color property, which acts as a global multiplier for the holographic color. This needs to be an HDR color, because I want the ability to make the rainbow super bright if I so wish. Then let's add a texture 2D property called holo color ramp. By default, if this texture is unassigned, then it uses a fully white texture, which is what I want. Next, I want to add a Boolean keyword called useColorRamp. When this is ticked, we're going to sample the color ramp texture to get our holo colors, and if unticked, we'll generate a rainbow inside the shader. The default values are fine. The shader feature setting means that a material always uses the one route through the shader corresponding to whether this is ticked or unticked. Multi-compile would let us change the value at runtime, as Unity compiles all variants of the shader. If you've ever waited an eternity for compiling shader variants to finish, this is why. First, let's drag the useColorRamp onto the graph and leave a bit of space to its left. It takes two inputs and outputs one of them depending on the keyword setting. I'm also going to take the animated value from before and pass it to an add mode. This is setting something up for later. When the keyword is on, we want to take this add and use it as a UV offset along the U-axis to sample the holo color ramp texture. When the keyword is off, we're going to take a fully saturated red color and use a hue node to cycle it from red to orange to yellow, green, and so on through the rainbow. If we set the range to normalized, then it will cycle the entire hue range when the input goes from 0 to 1. Finally, we can multiply by holo color, the global holotint property I added, and this part of the shader is done. If we quickly output this to base color, we can see what it's doing. It's a nice pattern, but this isn't quite what we want yet. I still want the rainbows to appear in streaks. Essentially, I want to define a direction for the streaks to appear in, and this is going to be flush with the card surface. I'll add this as a graph property called holoDirection, which is a vector 2, but for the maths, let's call it vector A, which I will normalize. As it's flush with the card surface, we can say that this is in tangent space, and if we expand it to a vector 3, its z component is always 0. Next, we need the view vector, v. This is the vector between the camera and the pixel being rendered, and it's normalized and also in tangent space. Then, to get these lovely rainbow streaks, let's take the dot product between v and a. Eventually, that's going to get us a pattern like this. I think the results speak for themselves. Then I added a float property called holo offset, which is a slider value between 0 and 1, which lets us control the neutral resting position of the streaks by adding it to the v.a result. I want to be able to configure how quickly the streaks move across the surface when you move the camera. Since I want to shift the whole streak uniformly, I can't just multiply the v.a value, because this would stretch the pattern, as different pixels have slightly different view vectors. Incidentally, I do actually also want control over that, so I'm going to add a flow property called holodensity and make it a slider. Then we can use it to multiply what we have so far. Now we're able to make big or small streaks. But for the rotational speed control, we will need to do a similar set of calculations as the streak dot product, but using a different input vector. This is going to be the offset between the camera position and the pivot point of the object being drawn, which I will call vector f, why not? Using the camera and object nodes, we can get these values and then normalize them. Since these are both world space vectors, let's transform the offset into a tangent space direction with a transform node. The nice thing here is that this vector is identical across the whole surface, no matter which pixel is being drawn. Side note, since we are using Unity 6, we can enable heat map color node, which gives us a rough indicator of how expensive each node is, according to this list. Blue means it has a variable cost, like texture sampling, but aside from that, the lighter you get, the pricier the node is. Accessing variables is basically free, but the transform node is very expensive. Probably because under the hood, it performs a matrix multiplication. Good to keep in mind if you need to start squeezing performance a bit. Anyway, let's take the dot product of vector A from before with the new vector F to give us a sort of streak offset value. By adding a new property called holo rotation scroll speed, which I'm going to clamp from 0 to 30, and multiplying the A.F result, we have a lot more control over how the streaks scroll over the card surface. We just need to add these two values together. And finally, a sine node, followed by a saturate node, to clamp the values between 0 and 1, is the final puzzle piece to make our streak pattern. I love the result we've achieved here, it's highly configurable, but we can go even further. First, quickly, remember that add node I stuck on the graph ages ago and just left there? The one between the noise values and the hue calculation? This is where we can pop in the streak pattern. Since the streak values run from 0 to 1, the rainbow will now start at, say, red on one side of each streak, and then cycle through the entire hue range as you cross the streak, and then end at red on the other side. The last major thing I want to inject into the holo pattern calculations is a texture to use as a mask. If you check out real Pokemon cards, the holographic effect doesn't always appear as uniform streaks. They have patterns. There's a page on Bulbapedia which lists a few holofoil patterns like cracked ice, or sheen, which is essentially what we have made so far. But one of my favourites is Cosmos, which I saw a lot growing up collecting Generation 1 to 4 cards. It kinda looks like a sky full of differently sized stars. There's also this stripy pattern from the Sword and Shield era that I like, but it's missing from the list. Thankfully, it's easy to add this functionality. Let's add a new texture 2D property called holomask, which will encode the holographic parts of the card as white and the non-holo parts as black. You can also have semi-holo if you use shades of grey. Let's drag it onto the graph and sample it, and then take just the red channel and multiply it with the saturate result. Now we can put together the base color and the holofoil pattern using a LURP node. The A slot is the base color we calculated at the start. Then the B slot uses the rainbow color, and the T slot uses this holo mask texture output. Then we can insert all of this into the graph's base color output. We are now very close to being done. Some special cards, such as special illustration rares and some promos, have these etched lines that give the surface real texture. I'm going to emulate this using a height map texture, which encodes raised parts of the image as white and lowered parts as black. By default, let's make this texture black. We can sample it on the graph and then use its red channel in a normal from height node, which does exactly that. It converts the raised and lowered values into a normal direction. Just make sure the node is in tangent space mode. I also want control over the strength, so let's add a float property called height map strength and make it a slider between 0 and 1 so that we have a nice value range in the material inspector. It turns out that the normal from height node is quite sensitive, so let's multiply that strength value by 0.002 before using it in the node. The result can be used for the graph's normal output, and we're done with the graph. Now we have a holographic card which you can rotate around and marvel at the way the light reflects and refracts across the surface with parallax layers. Oh wait, there's still some runtime left in the video? Huh, that's weird. Okay, I guess we can do some gambling. Hi. We're gonna do some unboxing. It's gonna be fun. Just a bit of fun. Today I have 3 packs of prismatic evolutions. I had to pay £8.50 for each of these packs, which is a travesty. Have my binder that's full of a lot of cards, but front pages, of course, the best Pokemon, Mimikyu. Fight me if you disagree. I have a lot of different Mimikyu. It might be an obsession at this point, but I don't care. Look, it's beautiful. The best Pokemon really is actually just... It's actually just Geese. So that's a magic card. And then the funniest Pokemon card I own, this guy. I'm just gonna flash and like prices somewhere on the screen, maybe here. Here's a very rare card. It's very expensive. The quality of this card is very poor. I bought this for £3.50 off some kid back in like 2008. I lost it for a few years and I had no idea where it went. And then my mum found it. It was in a sofa that we'd kind of like thrown into the back garden and just kind of hadn't disposed of yet. It's very water damaged. And the reason it's the funniest card I own is because it's water damaged and fused to the back of a base set Charizard. Which itself is worth a few £100s. They are inseparable. They are the same card. They are one card. And I'm gonna get sod off from these packs, but it's gonna be fun anyway. Right, I'm gonna do my best to open these slowly and carefully. It's exciting. Now, the one thing I didn't think about when I set up my camera here is, in fact, like, we're gonna see the cards backwards to each other, so I'm probably just gonna have to flip the video. Sorry. It's a Duraludon. It's a baby Dialga. Professor's Research. Hippowdon. Big sandy boy. He's a trunk. Amaris? I'm not even sure I know who this is. Professor Churro's Scenario. Oh, it's your king. It's your boy. It's Slow King. Okay, a glass trumpet. I can't imagine that would be very practical in real life. A Carmine. Then we have Sneasel. Is it the last? Am I keeping count? Is this the last card? It's a Monkey Dory. And we just have a Darkness Energy. Right, pack number 2 of 3. Let's go. Black Belts Training. And then we have Frolu. Oh, all the furrows in the chat. Rise up. Professor's Research, again. It's just a duplicate. It's cool. Duskull. We do stand ghost types. They are pretty cool. Ghost type? Dark type? Oh, maybe I'm being really stupid. Well, it's not dark type card. I think it is ghost type. I can't remember if it's also... I mean, it must be dark type because it's Duskull. That'd be dumb if it's not. Sea King. We've had a lot of kings. And Kieran is the other character from the DLC that I didn't play. An Executor. Not a Lowland, so he's not a long boy. Oh, another Black Belts Training, but this time it's reverse holo. Now I can see like a glimmer of like fancy colors in the next card, so that's exciting. What we got? Ooh. I got a special illustration rat. Oh, nice. Look at Flareon. He's pretty cool. Flareon isn't... I mean, let me see it a little bit closer there. Flareon isn't my favorite evolution, but like, they're all pretty good, right? Well, if I did collect Pokemon as an investment, this has paid for the 3 packs pretty handily. That's cool. I didn't expect to get anything from these packs, but Flareon's cool. Oh, and there's another card as well. I didn't expect to get anything. Oh, an Archelodon. So that's the bridge. Bigger baby Dialga. And a fire energy. Like, go nice with the Flareon. Alright, let's get pack number 3. Badoo. Here's my buddy. A Baneri. Thank God it's a Baneri and not a Lopunny, because I know what you Pokemon fans are like. Aloha Powdon. We got a Pinsir. Oh, so we got a few Kings. And we got a Surf. Buddy Poffin. A bug catching set. That'll go nice with a Pinsir. A Pyroar. Who would win? One of every Pokemon or a Pyroar? No, it's a billion Pyroar, sorry. A billion lines. I'm getting the meme wrong. A Groudon. Hey, Groudon is one of the cooler legendaries, I think. He is pretty sick. Another reversal though. Oh, this is one of the special ones. It's you can't see that really here, but if I this is the content. I've just made a video about fancy holo patterns, and I kind of got one. It's a Pokeball reverse one, and I got a Litleo that goes with the Pyroar. I know I got another fat over. I think it's just is this a regular illustration? I don't know the difference between a regular illustration of hairs and special ones, but like this is cool. I got another fancy card. Cool. Well, thanks for watching. Maybe I'll do this again sometime if this is my luck when I'm doing it for camera. Thank you for watching, and I hope you learned something in the shader part of this video, which is kind of the important part. Until next time, have fun making shaders.